So the objective of this afternoon is to switch a little bit from flows which are steady in the mean, like gas turbine flows, to flows which are always unsteady because they depend on time. The first one will be IC engines, and then I will show you another engine which is a new concept, which is like a hybrid design between an IC engine and a gas turbine. So let me begin by these IC engine questions. So you know that piston engines, we have had already talks about this problem here. You know that that's a critical problem for pollution, probably more than aircraft are, because the pollution levels associated to cars, of course, are stronger, but also they are more regulated. So there's more research there to make it work. And this research relies more and more on simulations. Even so, simulations are extremely difficult here because of the fact that this thing, even the geometry is fully unsteady all the time in an engine, in a piston engine. Now, the main thing I want to discuss today is not really the detail of engine combustion, but really the fact that engine combustion, piston engine combustion, also has all kinds of instability problems. And this was mentioned also yesterday by Professor Agarwal. If you're looking at an engine and you're computing the mean cycle, but all cycles differ from each other, it's going to be very difficult to do a good job. And that's what I want to discuss today. Now, in this field for piston engines, LES is becoming also the reference method, but it takes more time than in gas turbines, just because the technical problems of piston engine simulations, these problems are more difficult. So I will focus today on direct injection engines, on instabilities, and I will describe recent LES results to show you how we do these things in France. Basically, the message here is that if you want to do LES for piston engines, the first thing you need to do is to build a special experiment. Okay. You want to validate the LES. To do that, you have to talk to the people doing the experiment and ask them to do the engine you want, because the engines they do cannot be used to validate LES. So that's actually a big project called ECAMDAC here. And this project was about LES, but I would say 80% of the money went to the experiment. So indirect injection engine, that's the general context. You've seen already what that is. Instead of injecting the fuel upstream of the valves here, we inject it directly into the chamber. And that's a great thing to do because you don't have to burn in a fully premix mode. You can save fuel, but at the same time, of course, it raises all kinds of interesting questions. The idea is to go to lean combustion, and the idea also is to stratify the charge, which leads to a very different type of flames here. So it's good for many things, but it's also bad because you cannot work only with stratified flames, and you also need to be careful because you start making soot, because if it's not premixed, you start having very rich zones which will make soot, and the whole flow field becomes very important. You understand that if you inject air and fuel separately, if you don't put the fuel at the right point at the right time, then the fuel will not be where you expect it when the spark will go. And so the flow field becomes extremely important. So this is a very useful method to downsize the engine, to decrease the fuel consumption, but at the same time, we're going to have other problems here. And I won't talk today about knock or rumble. I will talk only about cycle-to-cycle variations. I will just show you a picture later, but as you know, among all the unpleasant things which may happen in an engine, where cycles are different, is that one cycle from time to time might start to knock. And if you have knocking in an engine, that's absolutely a bad idea. So we have seen that steady combustors like gas turbines can exhibit instabilities. It's the same thing for a piston engine. The difference is that in a gas turbine, what we see is that the flow will oscillate in time, and in a piston engine, what we'll see is that cycles will be different. So, and of course, the worst case in an engine is to have a cycle which burns and the next one does not. And I will show you many examples today where this happens. And then, of course, you imagine that if one cycle does not burn, you release all the fuel to the exhaust, and that's not going to help in terms of pollution. So images of cycle-to-cycle variations, those are, for the moment, experiments. the spark is here. Those are 4 different cycles at the same crank angle. And you see that they are different. And this means also that this is the curve we're going to use in most cases here. This is the pressure curve. In an engine, the pressure curve goes up like this. And if the engine is not fired, it comes back to this. If the engine is fired, you produce work, and that's what you use to push the car. If you plot many cycles on the same thing, you have here the maximum, the most efficient cycle. Here you have the cycle which burns at the minimum level, and all the other cycles are here. What you do, you compute the work produced by the engine, which is called the Emap here. And the Emap, you can take the variance of this quantity, which measures the spreading of this curve. And this is what we'll measure to define what an engine is in terms of stability. So if this thing is less than 2%, that means really the integral of this curve. If it's less than 2%, you say your engine is stable. And if you have typically more than 2%, you say the engine is unstable. So the engine that you have in your car today has probably a limited level of CCV, less than 2%. Otherwise, you would not find it on the market. Because when an engine is unstable, it's very difficult actually to drive it. It becomes a problem. And that's why actually many good concepts of engines do not make it on the road because they are too unstable. It's exactly like gas turbines. You have a great gas turbine, but it's oscillating. You cannot do anything with it. Another image of an experiment showing also that certain cycles might be burning very fast while other cycles are not. Even the things you see, and I'll come back to that today many times, you see that what happens quite often is that these flames get split. When turbulence is intense, there is no reason for the flame front to remain one ball of flame. Quite often it becomes 2 balls or more. And when it does, each ball now is more sensitive to stretch and may actually quench. And that's what's going to lead to problems of variations. Now the reasons why we have cycle-to-cycle variations in an engine are well known. One first reason may come from the outset, from the outside of the engine. For example, you don't inject the same amount of fuel, or you don't inject the same amount of air. Then can be, of course, that's a big topic. This is a turbulent flow. Turbulent flows are chaotic, so maybe for one cycle you have a certain structure, and for the next one you have another structure. And then you can have, at the spark plug itself, which is of course the sensitive point here, you can have a different composition. And if you have a different composition, then of course when you spark it, well, you have a different flame. There's a last but not negligible problem here, is that the spark itself may not be a process which is fully repetitive. You have to load the electrical circuit, then you get the spark, and from cycle to cycle, this thing may be different. We won't talk about that here because for the experiment, like as for the simulation, we used plugs which were really repetitive. Now, what causes cycle-to-cycle variations? If you have a stable engine, you want to make it unstable, there are different ways to do that. One of the methods is, for example, to increase the level of recirculating gases that you inject in the engine. So if you start from 0, you have a stable engine with a 2% variation, and then you increase the dilution here by burn gases in the fresh gas. Then at some point, shoop, these things go up, depending on the engine, but that really tells you that here, at 20%, you cannot operate this engine, okay? It's not going to work well. The other thing you can do, of course, is that you can try to run lean. Here, this is the occurrence ratio of an engine. At 1, you're stable. And if you try to go, to 0.6, you start seeing CCV, and at 0.5, the engine doesn't work well. When you have a level here of 20%, again, it means that certain cycles just don't burn at all. Now, when you have a high level of CCV, the vehicle becomes very difficult to drive. You increase the fuel, it makes more pollution. The engine may suffer if you go to knocking, so of course you don't want to do that. So you want to, and that's what everyone's trying to do in that field, you want to suppress them. To suppress them, you may try to suppress them blindly, or you may try to understand them, which is, for us, for our community, of course, the best way. For engineers, sometimes, if you can fix a problem and make money out of it, it's sufficient. But let's say for scientists, it's not. So how do you study CCV? Well, we're going to use an experiment which was developed specifically for LES in Paris here at IFP. And we're going to use simulations. Now, in terms of simulation, I don't need to convince you. We are not going to do runs, because runs cannot do something else than the mean. We are not looking for the mean, we're looking for the perturbations. Even so, certain people like Converge, again, Converge is trying to convince everyone that they can do CCV with ones. By the definition of ones, it cannot do CCV. It's going to give you the average cycle, that's all. DNS, of course, you're not going to do that in an engine, so we are left with LES, not much to do. Just a comment here, what we saw during this big project, which lasted 4 years, the main problem is to make sure that the guys doing the experiment give you the data you want and actually operate the engine that you believe you are operating. In my group, there's a big, let's say, a big COM that I've been using all the time. I keep saying if we do 100 simulations, out of these 100 simulations, 90 are not computed on the right geometry. And for the 10 which are left, 9 are not computing with the right flow rate. Okay? And if you can eliminate when you do LES, or actually CFD in general, if you can first make sure that you get the right geometry, and that then you get the right flow rate, you're in a much better situation. But in most cases, what I do, I send my student to the place where the experiment is taking place. He goes there with this rule, he measures things, and every time he says, oh, but that's not what you told me. You have changed this injection, and the experimentalists say, of course we had to, for a good reason. But why don't you tell me? Well, I forgot to tell you. I thought it was not important. And he has changed the geometry, and you're not computing the engine you believe. And this is actually the most important problem, more important than the turbulent combustion model, is to compute the right engine. Looks stupid, but believe me, it's a major problem. So the state of the art, when you look at LES of CCV in engines, is that a lot of people are studying that, but it's very difficult to do because you need to compute successive cycles. And computing many cycles one after the other takes a long time. And most people will do, maybe 10 cycles, 13 cycles. If you want to do statistics on that, it's really not much. So that's for the non-reacting cases. Of course, when you go to reacting cases, in the literature, it's going to be even more limited. That's with two-phase flow, non-reacting. And that's for reacting flows. And in the field of reacting flows, when we started this work, there were only ones done on 10 consecutive cycles, because, of course, if you want to do that, you must compute the whole cycle. Intake, compression, combustion, exhaust. And so even that, even in once, can be an interesting exercise. So there's only a few work then which deal with CCV. And in most of these studies, the idea was just to prove that you could do it. But there was no real validation. This is why we started this project, because we wanted to compare with an experiment. So the experiment was built to do that. So it's not as if we take an engine and try to see what it gives. We chose the system. So this is the engine. And the first thing you have to do is make sure that you understand the boundary conditions. So we forced those guys to remove everything they had, and we told them, we want a plenum here where we know what the pressure is. We want a plenum here at the outlet where we know where the pressure is. We want to know exactly all the geometry here. And we don't want anything fancy. We don't want a filter. We want to know exactly the whole geometry. And we want it premixed. That was the other point also. Before doing the direct injection, the first exercise was to say, let's make it premixed. So in that case, there is no mixing question. Can we do it? Can you capture what's going on? As I said this morning, if you do it premixed, we are mixing here the air and the propane. So the whole thing now is premixed. So you need to put a flame arrestor. Otherwise, the experimentalist might hate you, okay? Which means also that we're going to put the flame arrestor in the simulation, so we need to model it. So we had to model this guy. Otherwise, we could not capture what's going on for acoustics, for example. The engine itself is a 4-valve engine with optical access, and we had PIV, OH, and chemiluminescence. And every time you see PT somewhere, means we measured pressure and temperature, resolved over the cycle. So we have to compare all this data. Now, it's a nice setup because now we have we do have all boundary conditions. So you recognize here the flame arrestor. That's the inlet plenum, that's the outlet plenum, that's the engine. And this is what you need to compute, okay? So you see here the intake. You recognize it's LES now because you have your eyes adjusted to what I tried to tell you. If it's LES, you must see structures. Now you see structures, okay? If you do the same thing with ones, it will all be smooth. Next cycle, etc. remember that this is not a real engine yet. For example, it's a single cylinder. And of course, we do it now. We can compute a 4-cylinder. If you want to do a 4-cylinder, you're not going to validate much, because the experimental data will be insufficient. So it's really a problem to find the right equilibrium between a realistic engine and an engine on which you can do good measurements. So we stick to this single cylinder. So you have an optical window here. This has been described yesterday by Professor Garwal. You have a transparent piston. You can look at the flow from the bottom, and you can do all kinds of diagnostics. Those are the dimensions. This is a 500 cc, I guess, displacement engine. So I'm going to talk about, there's a huge database which was created for that, but I'm going to talk only about 4 cases. The first one is what we call the motored engine. That means the engine is not fueled. It's just rotating because of an electrical engine. And you can look at the non-reacting flow. And the rotation will be 1200. And of course, there's no instability there. There's no combustion. Okay. Then we'll talk about the reference case. The reference case is what we call stable ref, which means it has a low level of CCV. That will be used as a reference. And then we'll do a case where we dilute the intake gases by nitrogen. And here, you see that the CCV goes to 8%. So that's an unstable case. And then the last case we'll do is that it's called unstable lean. We'll decrease the occurrence ratio from 1 to 0.58. And then, of course, we'll go to 9% cycle-to-cycle variations. And the fuel will be propane. So again, no problems with atomization. We are not going to be able, it's an atomization problem because there is no atomization. It's not a problem of mixing because we do premixed. So we limit the number of things which can cause cycle-to-cycle variations. So let me show you first the setup. I will show then the simulations and go later to the analysis of these things. So LES strategy, you've seen that objective is really to see what's going on here. But if you want to see what is going on here, you need to measure the whole thing down to a point where you know the boundary conditions. So that will be this zone here. And of course, we could compute only on a small part of the engine. That would be easier. But then the boundary condition will be very difficult. So when we do the whole thing, for boundary condition, it's clear. We go to a place where pressure is imposed. Pressure is imposed. Simple. The problem, of course, that you need to model everything, and you need to add the flame arresters because they are there. So initially, we didn't put them in, and we saw that that was not working. The code is always the same. It's the same code we use for gas turbines. It's just that it can handle moving mesh. That's the only difference. Just a comment about piston engine codes. They are a little bit different from gas turbines because when we compute one cycle, we basically interpolate between phases. We create 40, 38 to 42 meshes, and we distort the mesh, and when the mesh has moved a little bit, we interpolate on a new mesh, we compute, we stop, we interpolate, etc. So the process is very long. The number of points vary, but it's not very large. If we do a gas turbine with 2 billion points, here in a piston engine, especially at top dead center, there's not much space to compute anyway. So we have meshes between 1 and 10 million points. So we cannot really make up for time because we have to wait for time to go by, because if you want to do multiple cycles, you need to repeat this thing in time. So it's a little bit painful to do this computation if you want to do a lot of cycles. The subgrid-scale model is the Smagorinsky model. Here we use Lax-Vendroff, which is not that good, second order in space, but again, if you want to be fast enough, it's necessary. We use law of the walls for heat and for fluxes. The flame arresters are modeled as multi-perforated plates. We worked on that a few years ago. We have a model for that can be included in the formulation. And of course, all the boundary conditions are characteristic boundary conditions that we described before. This is the good thing about teaching for 30 hours. Now you should know most of the things I'm referring to. So this is the mesh. The first thing you do in this system is to do what we call a mesh-only one. So just to visualize the mesh and see how it's moving. So the mesh is actually deforming, and as I said here, and maybe you can see it. I'm not sure you have the resolution to see it from where you are. The mesh is changing from time to time. You can see small jumps. This is every time we have an interpolation, then the mesh changes a little bit. and there are about 40 moments in one cycle where we change the mesh. One of the big problems, of course, is how you handle the opening and the closing moments in those valves. When you open some of these valves, normally you have a shock here because the pressure ratio is more than 2. So, and this is so you have a small shock over 2 points or 3 points. So they are dirty details here that most companies won't tell you, but you have to do things which are not especially nice to have the code do these things. There's a new thing also compared to gas turbines is that now at every cycle you need to ignite. You smear it out. That you say it's not going to last long, so I just put artificial viscosity and I wait until the pressure goes down. Yeah, approximately constant. Well, we add points, okay? That's the interest of interpolation. When we go to a bottom dead center, then we have much more points than at top dead center, because as I said, 40 times per cycle, we change grid. We stop the computation, we take the result, and we go to a new mesh. We do that 40 times per revolution, yeah. So to have enough precision, because again, the LES mesh must be very regular.
So then you have
20?
You have 20 different meshes?
Yeah, oh yeah. You start by creating 40 meshes actually. 40 meshes. And the way it works is the following. You have one mesh at one instant. You have what we said, the initial mesh. This mesh will be deformed. You pull it here until it goes to that point. And at that point, you interpolate on the new mesh, which you will again pull until you reach this point, and vice versa. So you create all the meshes. You create the initial mesh and the final mesh every time. And then you interpolate, you stretch the mesh in between. The whole procedure used to take about 5 months. Yeah, well, the new mesh is always cleaner. It's after you pull it a little bit, it gets less clean, and that's when you decide to change. Every time a mesh gets a little bit too distorted. The remeshing is automatic. That's not a problem. We do a high order interpolation. That works well. Well, we use exactly the same thing, IFP as a WANS code. This is the same procedure they use for the WANS code. There's no difference. Yeah.
So you said the pressure signal is averaged and imposed at the inlet. So usually in combustion engines, the intake manifold pressure itself varies very drastically, because of which we can have very many changes. And
sure. Yeah, the intake pressure here, but in the plenum, we compute the plenum up to this point, and in this point that the pressure osmote doesn't change. It's the same for the outlet. That's why we wanted these big plenums. Otherwise, you're right, if you want to do it only here, the intake pressure here is fluctuating. That's painful. There was another question.
What is the interpolation scheme that we use?
The
interpolation scheme?
Or we use third order schemes to do the interpolation in space.
If there are errors in interpolation, which there will be,
Yeah.
will they not act as triggers for instability?
Yeah, that could, and it could also even lose mass or gain mass or lose momentum or gain momentum, and this we checked many times by plotting the integral quantities. For example, the mass is perfectly conserved during these phases. That's all the numerical job which we have to do to make sure that this system works. But you see, it's the same problem if you use cut cell method in Converge, conserving mass. It's an interesting question.
Generally, most of the engines these days are either turbocharged or, in that case,
Yeah.
we cannot have a plenum straight away.
Sure, that's right.
We have to model the turbine part as well as this dashboard.
Yeah. But actually, the turbocharger is probably a simpler case, because then you know that there is a high pressure somewhere, and you can use that as a boundary condition. But then again, you would need to know the impedance of the turbocharger. That would be a complication. But again, this is why we built this case. This case is designed so that you can compute it. It's not necessarily designed to be a real engine. What we want to do is validate LES, not look at the physics of this flow, you know? Because, for example, it's a fully premixed engine. So who would use that? So again, our objective is to see if the computations can do it. Okay, the additional problem, of course, here compared to a gas turbine is that we need to ignite now at every cycle. In a gas turbine, you ignite, you know, you will forget the initial conditions, so you don't really care about the details of the ignition. In a piston engine, you have to care because it's going to play a big role. The other thing which is different also is the chemical scheme. So we didn't have to worry about that. And for this problem, you will see that, of course, things are a little bit more complicated. So spark ignition, I will talk about it tomorrow. Spark ignition is extremely complicated. Describing the initial plasma phase and all that is a very tough job. So for a problem like this, what most people do is to neglect the plasma phase and say, okay, we can have 40,000 K for a few nanoseconds. I begin after that. What's important for me for the flame is that this thing is releasing a given amount of energy over a certain amount of time. And
Why it's not important for gas turbine to see how spark propagates?
well, let's say that in a gas turbine, if you're looking at steady state, you don't care about how it was ignited, okay? Because you ignite it only once, you could use anything to ignite it. Here you ignite it at every cycle, so if you have a wrong ignition procedure, it's going to be contaminating the whole simulation. Now, of course, some people in the gas turbine community are specialists of ignition, you know, and then they have the same problem, of course. They have to model the igniter. So what we do here in those models, we have a model called the ED model, which was published a few years ago. And the ED model basically gives you a Gaussian in space and time energy deposition at time t0 over a sphere of radius sigma r. And the total energy which is deposited is epsilon I. So if you know the energy, this thing will produce an energy deposition in the equations that will increase the temperature, and then the combustion model will take over. Which is, of course, not what a spark is doing, okay? But I will talk about it tomorrow. It's a different topic. So the spark in this engine is located here, and we will find the mesh in this zone, because that's a zone where the gradients will be very strong. So this is a zoom again on this zone here. You can see that the flame is resolved over, you know, 1, 2, 3 points, which is really the minimum you can have. Below that would be difficult. And so this is where we would deposit the energy, and after a while you will see this kind of flame starting and getting wrinkled. So this is a pragmatic approach. It does not take into account the physics of the plasma, and we cannot predict cycle-to-cycle variations due to the plasma phase. Obviously, this is not in our capacities. It does not take into account also the fact that the electrical circuit itself might not be perfectly repeatable. Now, chemistry. I said in the gas turbines part that the nice thing about chemistry in a gas turbine is that it's at one pressure and one inlet temperature and one equivalence ratio. Now, everything is changing in an engine. The pressure will go up, the temperature will go up, but still, you can use a simple scheme. We use actually a two-step scheme for propane because we were burning propane. So that's the equilibrium to get the right flame temperature. And with these two schemes, if you fit the Arrhenius laws, then you can obtain something which works all over the range that you need. So the cost, of course, is going to be much less, and that's the important thing for us. So let me show you the typical results. A good way to look at an engine like this for chemistry is to plot here the temperature or the pressure, because the two go together. Typically in an engine, when you compress the gases, it's an isentropic compression, so temperature and pressure go together. So the important thing is to be able to match flame speed over a range of fresh gases temperature, or equivalently over a range of fresh gases pressure. And you go here, you know, from 700, 600 to 1000, and you have here the two-step scheme which we used, and here you have two complex chemistry schemes, and interestingly, as I told you before, they don't agree. So even if you would want to take a complex chemical scheme, you wouldn't know which one to take. So we fitted to be in the middle. The difference, of course, is that this costs, you know, 1 and this costs 50. Same thing here for the case where we have dilution. So it's a case where we have EGR in the fresh gases. And again, you see that the two-step scheme, which is the same as here, is doing reasonably well until here there's a mismatch. But again, I think that's not the main problem we have in the simulation. For combustion modeling, we use the same model that you know, the second flame model. We don't change the constants. And so let me jump now to the results. So this is the motor case where you have no combustion. So you can see the sensors here, sensor 1, which is here, the 2, which is in the intake here, and the 3, which is in the plenum. You can see the turbulent flow, and now again, the trick is, the problem now here is that you can do this simulation, and then what do you do with them? Well, you have to compare them to the experiment. What do we have to compare? Well, I will show you in a minute that we can compare all the pressure signals all over the lines here to see if we capture them, and we can compare, of course, the velocity field inside the engine. So that's for a case without combustion. When you do combustion, I will show you here first an example just to give you an idea of the flow. This is a case with a high CCV, this is a case with a low CCV. When you just look at one cycle, it's difficult sometimes to see if it's low or high because you would have to compare the cycles. But by the way, you will see a few things here. Okay, so the first thing you will see is that we spark sooner in the high CCV case and later here in the low CCV. And then when you get combustion here, the flame really starts as a big flame right away and hot. While here you see from time to time, you see these two flames here. And then you see you have much more winkling here. Here, the winkling is much less. The flame is more compact, less sensitive to turbulence. That explains when you repeat these cycles, here you see many cycles one after each other. Here, many cases, you see a flame which is shredded into many pieces. And here you have a very robust flame, very spherical. Just a word about time steps for these simulations. That's for the reacting case. You have here the time steps in nanoseconds, okay? So the time step can go to values like 50 nanoseconds. It's small. So this is why these simulations are expensive. And the time step is changing, of course, versus time. There are moments where you can have a large time steps, but then when you have ignition, for example, you need a small time step. And when you have exhaust here, you have very large velocities near the valve, so you need to decrease the time step.
How do you dynamically define the time step? You initially impose it, or there's a way of calculating?
No, the time step is computed before the time integration by looking at the CFL and the Fourier and the chemistry. And you take the minimum values so that you satisfy all criteria. Now, the TFLES model the TFLES model, you have here the typical levels for thickening factors and efficiency. So you see that the thickening factor, which is the red curve here, can go up to 80 at certain moments. Makes sense. I mean, the pressure is very large. The flame, again, I mean, we come back to the discussions we've had many times. The flame must be 50 microns thick. So you have to make it thicker. Otherwise, you cannot resolve the flame form. And the efficiency now, the fact that you have thickened the flame, so you need to correct for it, that's the mean values. The efficiency is of the order of 2, okay? You need to increase the speed by a factor of 2, which is not big. It's not 50, but still it's not 0, okay, if you don't do that. Again, if you don't thicken, if you take 1 here, and if you don't do anything for the efficiency, you're not going to get the white flame. Now, a few analyses here of more quantitative problems. You have the 3 cases here. That's the reference case, which has a very big flame speed, actually, you see? 1.5 meters per second, that's the laminar flame speed. It's stoichiometric, it burns really well. Now you see that the 2 other cases, they have this first characteristic that the flame speeds are much less. So these flames are going to be more sensitive to turbulence. So that's not going to help them, okay? And that's actually the first factor. You see the same thing for the flame thickness. This flame here is very thin, it's very fast, so it's very thin, and so it's going to be very resistant. The 2 others have large flame thicknesses, and that may be a problem for them when they will be submitted to turbulence. Now, CPU time is also an interesting question. This is the CPU time per, let's say, millisecond of real code. And you see that certain phases are fast to compute, and certain phases are slow to compute. And actually, this one here, for example, is a critical moment. That's the moment where we open the valves, and because we have very large speeds, and this thing costs us a lot. The orders of magnitude, but this is changing very fast, okay? It takes about 20 hours if you have 400 pulses to do one cycle, and about 2 times that to do the reacting case. But, you know, those things, if you have more processors, it's going to cost less. So let's go to comparisons now. Look now at the intake duct. We are looking here at the reacting cases, and we look at the signals at that point. So this is, the engine is here. We look at the signal before you enter into this separation into 2 valve ducts. So you see that the green curves is the LES, and the black dots are the measurements. And you see that they are captured extremely well, okay? And even the shape, the trends are very well captured by the LES.
In your simulation,
Yeah.
you have taken sensors at 3 different locations.
Yeah.
Which component velocity are you using for acoustic? Is it the Y component or the Z component?
This is pressure.
Okay.
So for pressure, there's only one pressure. It's the wall pressure. It's the static pressure.
But for if I have to decompose and obtain the deflection coefficient.
Well, when you do a measurement like this, I mean, the simulation does not start here. The simulation starts somewhere here. This is just a result of the experiment. You have a microphone, well, a pressure sensor. You do the same thing in the LES, and you compare. So here, there's no boundary condition or nothing. You just directly get the pressure. You measure the pressure.
You do LES in the duct also?
Please?
The conduits?
Yeah.
LES mesh, LES.
The LES goes up to the plenum. I mean, we have meshed like 2 more meters here on the intake, and same thing at the outlet, to go to a place where we know that pressure is controlled, that the 2 plenums that we have installed on this system. Because we wanted to go to a place where there is no problem with boundary condition.
This is average over how many cycles? 2 cycles, right?
Those are averaged. Actually, I will show that in a minute. There is very few variation for these signals. So I'm not sure if we average them or not, but they almost don't change from cycle to cycle.
So my question was, I was checking the deflection coefficient in the exhaust.
Yeah,
So in experiment, I have a sensor. From sensor, I get the acoustic pressure.
yeah, you could, yeah.
But in simulations, if I put sensors all across, so sometimes I'm capturing the Z component, sometimes I'm capturing Y component. Should I take in all the directs only the Z component and use it to calculate reflection coefficient? Should I keep changing to all the
No, normally in those ducts here, everything is 1D. Okay, so you should take only the actual velocity. If there is swirl or things like this, you don't care. Normally, everything is 1D, so it's actual velocity and pressure, and that gives you the acoustic wave. There should not be any transverse modes here. Now, if you look at the exhaust duct now, so the engine is here, we go to that point. This is the reference case, and again, you see the pressure, and you see that the signal is very well captured. If you do the same thing, and you don't include the flame arresters in the intake, then you have problems. This is this curve here. That's what we had first, and we found out that we needed to put the flame arresters to get the signals right. Now, if you go now, the thing I did not mention is that the cycles have very, very limited variability in the intake and in the exhaust, probably because of the plenums. So we control that pretty well. And still, the pressure in the chamber has large variations. So if you look at the signals in the intake or the exhaust, it's almost the same all the time. But in the engine, with the LES, you get a very large variation, which tells you right away that you can have, doesn't mean it's the only source, but you can have CCV even if you have a perfect intake and a perfect exhaust system with no variations. The turbulence itself in the engine can do the job. Now, of course, when you have the LES running, the question is how do you compare the LES and the cycles? Well, you cannot compare individual cycles. Obviously, they don't have to match. So you have first to compare the averages, and this is what is done here. Here you have the pressure curves for the ref case, the diluted case, and the lean case. And you can see the experiment here, and here you can see the LES. And if you want to quantify that, you have to look at the envelope and start looking at statistics, which is what is done here. So in black here, you have the LES, and in red you have the envelope of the experiment. And you see that the mean values are pretty good, and that the fluctuations, that means the envelope is also very well predicted with large eddy simulation, especially here. For the cases which are unstable, LES also says, yes, there is a problem of CCV, and that was actually one of the things we wanted to see. Can you predict the fact that these two things will be unstable? The answer is yes, you can. If you use once for that, you will always find only one cycle. So you cannot do that with once. Actually, we've tried it. We have a once code too. If we run it, we always find the same cycle. There is no reason for that to change, because the once, again, averages over all cycles. Okay, let me jump here a little bit, because we're getting a bit late here. Just one point, which is, of course, very important. Once you set up the experiment, you can run thousands of cycles. It's only a matter of the size of the disk on which you store the data. But for LES, each new cycle costs you, okay? Costs you a lot of CPU. So an interesting question was to know how many cycles do we need to compare. In many cases, I've shown you we have been comparing 5,000 cycles in the experiment and maybe 10 in the LES. So you can actually look at, for example, the maximum pressure obtained in the experiment and obtained in the LES. In the experiment, you have thousands of cycles. In the LES, you have, 20, 25, 30. So there's one thing you can do is say, how many cycles do I need to get something which means something? So you can actually start, with the least you can have to do a cycle-to-cycle variation is to have 2 cycles. It's difficult to do less than 2. Huh? Then you can have 3, 4, etc. And what you can do is to put here the number of cycles on which you averaged, and then you do that on the experiment, you do that on the LES, and you look at the convergence of the statistics. And you see that, after 20 cycles here, the statistics don't change that much. That's the mean pressure, and for different cases here. And you see that you need, from 20 to 50 cycles. And but after 10 cycles already, you get the right mean pressure. So the mean pressure you can have with maybe 10 cycles. If you want to look at the variance now, you see that it takes more time to compute a variance. But typically, 25, 30 cycles, the LES is not far from the experiment, and it's converged. So the evaluation is that for this case, not necessarily true all the time. For this case, probably if you have 25 to 50 cycles, you're in good shape, which is already a lot, okay, because you need to get this thing running. What we've done also, we said, okay, let's start with 25. So if you do 25 here, that's one set of 25, but you can do it also in the experiment. In the experiment, you can take many sets of 25 cycles and see if, the results are the same. And actually, you can prove that the results are very close. This is the result here for the covariance of the IMAP, and you see that the stable regimes obtained by LES or by experiments are actually consistent. In other words, if an engine is unstable, you don't need to run 1,000 cycles in the LES to see that. After 25 cycles, the LES will tell you this engine is unstable. It's there. No need to continue the computation. So we'll say that probably 25 cycles is a good start to do this kind of statistics. Now, another question, of course, is why is this engine unstable? To do that, you can look at the experimental results, where you have chemiluminescence and PLIF. And you can look at the different cycles. That's what we have here. So this is for the reference case, the stable case. If you look at individual cycles, this is what you see. This is the experiment at the beginning, a little bit later, and that's the LES. And of course, you cannot compare. What you can do, however, is to compare the average of that. That means like the probability of finding the flame, and this is what you obtain. It's reasonably the same, but then I would say everything is so blurred that it's difficult to conclude. If you dilute these things, then it gets more complicated. This is the experimental results. This is the experiment, this is the LES. You see here that 2 cycles can be extremely different. So when you do averages, basically you end up with conclusions like, well, the flame can be anywhere in the experiment, and the flame can be anywhere in the LES. It's tough to conclude. So until here, what we've shown is that in this special engine, LES is probably a good way to do studies of cycle-to-cycle variations. And the question is, can we then use LES to do a little bit more than that? Especially what we'd like to do is to understand the sources of the CCV and to fix the problems. We know here that the sources are not mixing, there is no mixing, they are not two-phase flow, and they are not intake or exhaust characteristics. So they have to be linked to what's taking place in the chamber. So it's turbulence. So let me jump that too and go straight to this part here. Okay, so here you have a visualization of the flame contour for two types of flames, the reference case and the diluted flame. So we start at a crank angle of -51. You can see the two flames starting. And again, this is the reference case, and this is the unstable case. And you have to watch them for a long time before you start seeing differences. But there are differences between these two guys. One of the big differences is really that this one creates very often fragmented elements of flames. In other words, the flame is not always able to stick in one piece. Just another example here. Of course, you know that this flow is tumbling, and what we see is that the unstable dilution case, because it's burning less fast than the other guy, we need to ignite it sooner in the cycle. And at that moment, the tumble is very strong, and basically what we're seeing is that because the tumble is strong and the flame speed is low, this flame has a hard time, resisting to the turbulence. And that's, of course, a good reason for it to, for example, be separated in two pieces, and because it has a low flame speed, it will have a hard time recovering from that. And then the other problem in this engine is that the tumble is turning like this, so if you cut a piece of the flame, then you push it against the wall. You've seen this morning, if you push a flame against the wall, you're going to quench it. That's not going to help in terms of combustion efficiency. And then even if you don't quench it, this flame quite often is not going to burn reasonably fast. Now for the stabilized flame, it's a bit different because here you ignite it later, so the tumble is less. And the flame propagates very fast in the chamber because the flame speed is more. This is a stoichiometric flame. And the flame usually does not split. It stays in one piece. And then it starts propagating, and then it's a very strong flame, so it's very difficult for the flow to modify it. So as a result, this one burns almost every cycle in the same way, almost, and this one does not. The tumble motion is actually an interesting thing here. The tumble motion measures, it's like the swirl number, it measures the level of tumble in this flow. You see that for the reference case, because we ignite later in the cycle, the tumble is much less than what we do for the diluted case. In other words, for the stable case, the flow is turning more slowly than it is for the unstable case. And for the unstable case, unfortunately, the flame speed is also lower, much less than for the reference case. In other words, we have two things which go in the same direction. We have less flame speed and we have more turbulence. These two things together are going to affect the flame very strongly. And this is what...
Was it compared to any motors PIV tumbles of the...
This data, yes. This data, they measured from PIV. And this makes sense. It's going down because the flow is decaying. The turbulence intensity is going down, the tumble is going down. Okay. So that really means that the unstable flame here is more sensitive to the large-scale motions because the flow is turning faster and the flame is going more slowly. Okay, so if you look at the cycles now, the other thing we started doing is to look at individual cycles, one after the other. So you have here, for one case, you have the envelope here and you have different cycles, and you see that, for example, this cycle here, C4, is really a bad cycle, okay? It's not burning much. And the peak pressure is almost what you would have without combustion. Without combustion, it would be here, So this thing is really not doing a good job. So we started looking at this cycle and wondering why it was so. So this is a cycle which burns well, and this is a cycle which does not burn well. And you see that even at the end here of the combustion phase, there is some fuel left in the system, which is not good. If you look now at the movie, so that's the the cycle which does not burn well, you see here that one of the problems is that it's splitted into many flame elements, and that's not good for efficiency. So that when this cycle finishes, unlike this one, you have some unburned fuel left here near the walls, and that really tells you that the flame speed, the overall flame speed was not enough. Yeah?
The reason the device was not modeled because when we talk about incomplete combustion, it's a very important part. The trapped mass can change cycle duration.
Okay, I didn't show that the trapped mass is always the same here because the intake and the exhaust are always the same pressure. So when we monitor the trapped mass, it's almost constant. So it's not that there is less mass, it's that there is less velocity at the moment of ignition. That's in this case. Does not mean it's always like this, okay? For this engine, you don't need to find changes in the trapped mass to find changes in the combustion efficiency.
What about this food thing? Like somebody food is from will it be like modern something food attached to the wall?
So what do you mean? The wall effects here?
Yeah, the wall effect on the food particle. The food particle will be there in the wall something and that will be affecting the flame as well.
Well, normally this flame is not supposed to soot. It's a clean flame. It's a gas flame. So normally in this engine we should not have soot problems. That's also another reason to use gas. But in a real engine, you're right. That's an additional problem. But this is why we wanted to eliminate problems, not to add problems. Okay, so let me show you now what you can do also in the LES. And I don't know if we tried that. The thing we've seen in this cycle, which is not strong enough, is that it's really because it's ignited at a place where it's pushed right away against the wall. So we said, why don't we move a little bit the spark? For example, if we take the initial sparking point, which was here, in the LES, it's easy to put it 1 millimeter more down. And then we can repeat the simulation. And if you look now at the cycles, you see here that you still have the splitting, but the pocket which is here does not quench. And finally, this cycle starts burning much faster than that one. And the only thing we've done is to move the spark a little bit, by 1 millimeter. So that the interaction now between the flame, which is pushed against that point, is such that you don't cut the flame and you don't slow it down. Not enough, at least. If you look at the pressure curves here, you see here that just by moving the spark by 1 millimeter, you go from here to there. So it's also saying that this flow is extremely sensitive to details, and that anything you change here will change the efficiency. It's also telling you that when you think about designing an engine like this, you have to think about flame wall interaction, okay? Because this big tumbling motion is a problem here. You interact with the wall very strongly. Okay, I have finished this part. I just want to explain what I'm going to do next. There are also other places where people are trying to investigate chambers which look like piston engines. They're called constant volume combustion chambers, and that's the one I will describe next. Those chambers are interesting because they are almost similar to combustion engines, ICE, but they are not the same. So let me just introduce that, and then we'll take a short break. Okay, so here we touched this question already, actually, with Professor Kouchari, I guess, and you've seen also Professor Agarwal. You know that to propel, for example, an helicopter, the main advantage of using a gas turbine is the ratio of the power to the weight. It's a light engine, it produces a lot of power. But a few people have said, for example, if you go to a race which is called Les 24 Heures du Mans, maybe you heard about that, that's a race of 24 hours in France with cars, and you look at the engines there, you will see that these engines develop the same power than an aircraft engine, and they are almost at the same weight. And you can say, oh, those are race cars, they are expensive. Well, they are expensive, but not more than an helicopter engine. Okay, a gas turbine is also expensive. So a lot of people start questioning the fact that we use gas turbines for this thing. And for example, a diesel engine, a waste diesel engine producing 700 or 800 horsepower is much more efficient than a gas turbine in terms of consumption. Then the problem, of course, it's also a little bit weight heavier. But still, people are trying to find ways now to, try to improve on these things. There's actually an helicopter tested in Europe, a big helicopter with a big diesel engine. And this diesel engine has been designed by Peugeot, the guys who are racing at, on the road. So people are looking for better concepts, better ideas to propel aircraft. Among all these concepts, of course, the idea of using a car engine, of course, is a good one. But there are other ways. And if you look at the history, of course, of flights, that was said yesterday, I think in 10 years, everyone went to the jet engine because the ratio power to weight is extremely good. The problem with these engines is that they all use the same technology. They are all based on what we call a constant pressure cycle for combustion. So what does that mean? Well, if you just look at how these engines are working, you have an intake here, then you go through a compression phase, and here, when you enter the chamber, you are at constant pressure. Okay. So you go in this way in the diagram, and then if you continue, then you expand in the turbine, you go back again. And that's what we call the thermodynamic cycle of this thing. It's called a Brayton cycle, and it has a given efficiency. But that's not what you do in a car. You can do in a car, you can go to constant volume combustion. And actually, a few people in the world, well, different groups, in France, Germany, Purdue is doing that too, are looking for ways to install this, take this away, install another engine, an engine which should have more efficiency. To increase the efficiency, we know how to do it from, let's say, in theory. The theory tells you that if you want to move away, increase the efficiency, you have to change combustion. You have to go from a constant pressure combustion to a constant volume combustion. How do you do that? Well, when you reach that point here, you get out of the compressor. Instead of having this constant chamber, constant combustion, constant pressure combustion, you use a system where you block the inlet, you block the outlet, so now you have a constant volume chamber, and you ignite. Then the pressure will go much higher. And if the pressure goes much higher, you change cycle, you go to a Humphrey cycle, and this cycle actually will have more efficiency than the Brayton cycle. You can compute these efficiencies. So you can just, that's a classical exercise in thermodynamics. This is the expression of the efficiency for the Brayton cycle. This is for the Humphrey cycle. And if you put everything on the same plot, you see that for the same compressor, if you go from the existing cycle to the Humphrey cycle, you can go from an efficiency of, maybe 40% here to 55, which means that the engine of today could have an improvement in efficiency of maybe 25%. Yeah, okay. So I'm going to discuss now, in the second part of the talk, I'm going to present you an engine based on this concept. And you will see that it really looks now like a piston engine. And then it has the same problems, including cycle-to-cycle variations. One more, maybe 40 minutes, something like this, to talk about this engine, which is, as you will see, some kind of hybrid engine sitting in the middle between piston engines and gas turbines. So, once you've said that there is a potential gain in cycles from 40 to 55%, of course, everyone starts thinking, well, that's great. If you can increase the efficiency of a gas turbine by, 15% compared to 40, which would be 1/3 of the present engine, then certainly everyone wants to do it. So the question is, how do you do it? Okay, this is where things get complicated. There is one way, a first way to do that is to use supersonic combustion, so detonations. And I've shown already, I guess, these pictures when you can have a rotating detonation, and there are all kinds of people looking at that at the moment in the world, trying to use a detonation because the combustion is so fast that it's going to work exactly like constant volume combustion. This is not what I want to discuss today. I want to talk about subsonic. Okay, well, there's another one actually. There's also the pulse detonation engine, which is about the same. You fill a chamber, and then you ignite it, you create a detonation, the chamber is emptied, and then you start again. A little bit like the V1 was for the Germans, but with a supersonic flame there, detonation. So that's not what I want to describe today. I want to stick to subsonic combustion. And then there are different concepts. One of them is what is called the wave rotor from Purdue. And here, it's an interesting engine to have something which is constant volume. You have a combustion chamber which is turning around the axis of the engine. So if you are one of these chambers, these are small chambers here, you turn, so here first you arrive in front of the feeding part, so they feed you air. Then you continue turning, then they feed you fuel. You continue turning, then they ignite you. You burn, and then when you arrive here, they open your exhaust, you leave, and then they reopen the admission, the intake, and then you keep doing, okay? So that's why they call it a wave rotor, because this thing is actually turning. It's one concept to ensure that at the moment where you burn here, both inlet and outlet are closed, okay? Because this section here is closed by the outlet flange that you have here. And they have an engine which works like this. And the engine I want to describe today is based on a simpler idea, because we don't want to have this thing turning. We're just going to use a chamber and use valves at the inlet and the outlet. Okay? So this is a little bit like a piston engine without piston. Okay? If you would have a piston engine, you could have a piston here going up and down. So this is like a piston engine with no piston. And the idea would be to use that in a chamber like gas turbine. So you would replace these chambers here by these constant volume combustion chambers. Here, we would remove the existing chamber, and here we would put this constant volume combustion chamber. So it's an interesting concept. There's been quite a few studies in France about it, and I want to show you the results because they are fun, and because again, they bring us back to the problem of CVC. So that's a design of the engine. You see the shape here of the valves at the exhaust here and at the inlet here. How does this thing work? So these things are turning, okay? So you have fresh gases coming here, exactly like a piston engine. And when they are burnt, they go out through the outlet, okay? So normally on the paper, it's simple. You feed the system, you close the valve, you burn, you open the exhaust valve, it goes away, and you start again. For those of you used to engines, it actually looks a little bit like a two-stroke engine. Huh? You will see it has the same problems. So if you look at the different phases, you start here by opening the intake and the exhaust valves at the same time so that you can push the burn gases out and feed fresh gases into the system. Then you close everyone, inlet and outlet, and then you ignite this thing, you have combustion. And when combustion is finished, you open the outlet and you can push these gases out, and then you open the inlet and you purge the whole system. So here you push the burn gases out, and at this moment you restart. So the concept is nice. If you can make it work, you can go to constant volume combustion, so you can go to higher efficiencies. The question is, does it work in practice? So there's only one way to know that, is you need to do the studies, okay? You can do what I will call zero-dimensional simulation, but that's just thermodynamic computation. I won't describe them today. You can do an experiment, which was done here in Poitiers, which I will describe, and you can do an LES. And like always, the question is this engine working? And if it works, can we use LES to try to understand what's going on? So let me first describe the engine. So this is the engine here. You have, again, a plenum, which is working at 3 bars. Then you have a carburation chamber here, which is like a carburetor in an engine, actually. This is the place where we're going to inject fuel and mix it with the air here. Then you go into a chamber, and in this chamber you can see here the engines which are rotating the valves at the inlet and at the outlet. And then you go through an exhaust duct directly to the atmosphere. Okay? So it's a very simple piston engine without piston. So in this system, when the air arrives from the tank here, it's mixed with fuel, which is injected by injectors here, which are on the top and at the bottom. There are 4 of them. They will inject liquid fuel. It will mix with the air and go this way into the chamber where the combustion will take place. And here, combustion is ignited by a spark, okay, or a big spark. And then the exhaust is here. The shape of the intake valves and the exhaust valves was done to give certain pressure lows, and you can see the intake here and the exhaust here. For those of you who work on the Wankel engine, this is the same problem as the Wankel engine. The leaks here are a big problem. Okay, these systems don't close very well. You know, so we expect that leaks are going to play some role in this system. So this is the section, the area of the intake valves and of the exhaust valves versus crank angle. Note that in this system, there are 2 combustion events per cycle, per rotation, because the valves here are symmetrical. So when they do one turn, it's actually 2 cycles. So we just need to look at 180 degrees to describe the whole process. So this curve here is the section that is here. When this now it's closed, but when it's open, there's a certain area, and same thing for the outlet. So you see that there's a crossing, there's a moment where both valves are open, and that's dangerous. We know in an engine that it's not a good idea because you might be injecting some fuel which would actually go straight to the outlet, okay? Like in a 2-stroke engine. Bad for consumption. But for the cycle, you have to do that. And the exhaust valve is here, and you see that combustion is taking place at a moment where all valves are closed. This is the constant volume that we need. So it works like this. Here we exhaust the burn gases of the previous cycle. Here we intake the new fresh gases, and we at the same time keep pushing burn gases out, and then everything's closed and we burn. Okay, so the cycle will look like this, and the ignition will take place, of course, somewhere here. Just after we close the valve, we're going to ignite this thing. Now, if you take a look at, there's a quartz window in this zone, and you can take a look at the flame, and this is the moment of ignition. You see the flame growing here. That's the blue zone. And by the way, you recognize that it's doing a few things. It's sooting a little bit, which is not a good starting point. And it's also very turbulent, that we expect, because the flow is going very fast. So we're going to have to deal with a very intense level of turbulence. And in there, we are using the spark. You can see the spark. It's this guy here. It's a very intense spark. And one of the questions is, like in an engine, we don't have that much time before we open the valves, so we need to finish the combustion rapidly. So you need an intense turbulence to do that. And so the whole problem is to tune this thing. So how does that work? Before I talk about that, I need to describe the injection. We inject here actually through these 4 injectors, which are located upstream of the chamber. And this is done here. So the injectors work sequentially. So the first injector starts here, then the second one is here, the third one, and the fourth one. You inject while the previous cycle is actually burning, okay? This is the combustion phase of cycle N-1, and this is the fuel injected for cycle N, okay? Which will then be admitted here and then will burn in the next cycle. So it's a little bit crowded here, okay? You have to do everything in a short time. Okay, so the first thing which happened when they started doing that is that they saw that they had a lot of problems. After they fixed the first problems, they basically changed a few things. The phase between the valves, the ignition angle. So the phase, I need to decide to define this. The phase between the valves is the difference of angle between this point and that point. Okay, that's the center of the opening of the exhaust valves and the center of the intake valves. That's what's actually used to trigger the 2 valves and the electronic control of these guys. They did different rotation speed, 1200 and 1500. They changed the ignition. They changed the spark intensity. So we're going to work mainly on these 2 cases here because those are the ones we computed. I'm going to show you non-reactive cases, and then I will show you reactive cases. And if you look at the pressure now, remember this is the intake, this is the exhaust. If you look at the pressure, this is what you find, okay? This is experimental. Now, everything is normalized here by the intake pressure, which is 3 bars. So what you see is that when you open the outlet valve, the pressure in the chamber is about 2.7 bars. Since the outlet is at 1 bar, the pressure goes down. Okay? Then when you open the intake valve, whoop, there's more mass coming into the problem. Then you stop here injecting, you close all the valves, and the pressure goes down slowly, and then you restart your cycle. There's no combustion here. You see something here is that that's a technology problem. Here, this curve is slowly going down. Even so, the inlet valves and the outlet valves are closed. So that's telling you you have leaks. Okay? And that's really a major problem in all these systems, is that if you have something turning, like in the Wankel engine, being able to avoid leaks is a tough problem. It's not our problem, but it's a technology problem. So if you do multiple cycles for this flow, you find that that's the maximum pressure you have, the minimum, and this is the mean, and you see there's actually very few dispersion or variations, so it's almost always the same. And so it's a repetitive process. It's not going to be like this with combustion, but without combustion, finally, it's a very steady process. So we know where it's leaking. It's leaking, of course, near the valves. Okay? So there's not much you can do about that. But the volumetric efficiency is of the order of 94%. The volumetric efficiency is the ratio of the mass, of the trapped mass you have at one moment, compared to the trapped mass you would have if you would, wait forever so that this thing fills up. So it's not too bad. 94% is a reasonable number for such a new chamber. Now, this is the cases with combustion. And now with combustion, things are different. We ignite here just at the moment where both valves are closed. And when you do that, this is one pressure cycle. Now it's always normalized by the inlet pressure. So you go from 3 bars here. This is 3. And then you go here typically to 13 bars. If you do simple computation of final pressure, you see that 12 bars here is not enough. For this case, we should have gone to 17 or 18. And you will see this is due again to leaks and to combustion, which is not sufficiently fast. So if you do another cycle experimentally, this is what you get. Another one. And you see these cycles start showing something that we have seen. Now I'm showing here 50 cycles. What we have seen for an engine is that you have a lot of cycle-to-cycle variations, especially in the combustion phase. Even so, at this point here, when you ignite, the pressure is the same. That's an interesting problem. The pressure is the same. The equivalence ratio is the same. Then suddenly, certain cycles will burn very fast, and certain cycles will actually almost not burn. So we again hit this problem of CCVs. That's the maximum pressure in the system, and that's the minimum pressure in the system, and we'll use that for LES to see where we are compared to the experimental data. So let me skip that for the moment. The important question was, why do you have these cyclic variations, and can you limit them? And why don't we go actually to the maximum pressure? We should have gone to 17 bars. Actually, if you go only to 12 instead of 17, the efficiency will not be good.
The chamber enclosed, how is it ensured that the heat transfer?
That's the other thing, which of course leads to lower pressures, is the heat transfer to the walls. That's the one other reason why the maximum pressure does not go to what it should be. You have a question? Yeah. There's a backflow. Yeah. There's a backflow. Not only a backflow, but if you're not careful, the flame does that. You have a flashback. No, you don't see it here. You will see it on the movie. You can have certainly there is a backflow. Yeah, that's many. Well, this is the people in the gas turbines. They are beginners in the field of valves. So they're just learning what people in the piston engine companies know. So why don't you get the maximum pressure? Well, you can have a problem first, is that you don't have the fuel you believe you should have, because it's like a two-stroke engine. There's a moment where both valves are open, so the fuel might just go in and leave right away. Don't burn it. So that's a good reason not to reach the efficiency you want. You can have also other problems like, is this thing working? Yeah. You can have a slow combustion. Maybe combustion goes too slowly so that when the outlet valves open, it's not finished, and you just push your gases away. So then you lose, of course, the efficiency. I forgot one thing, of course, the heat transfer to the wall will also decrease the pressure.
One of the reasons two-stroke petrol engines were sent out of the market was mainly this, that the inlet port and the exhaust port were always in front of each other. That was thereby causing a lot of pollution.
Yeah.
Even though the efficiency similar to this, there were two power cycles in 7 to 3 and there was a lot of efficiency in them. The pollutants wise, I mean, this looks very similar to that. So
Yeah.
but the pollutants drag the
Yeah, except you know that for gas turbines, the regulations are not as tough as for piston engines. So maybe this would still pass the regulations for gas turbines. But I agree, I mean, that many things here look a little bit like a two-stroke engine. And the second question is, why do we have cyclic variations? Of course, it's a stratified flow in the chamber, and maybe at the place where you spark, you don't have fuel. It's just a bad idea. The other problem, and I will come back to that, and it's also connected to what we have learned, is that this is a very turbulent flow. There's a very important difference between this flow and a piston engine. In a piston engine, when you close the valves, you still have a long compression phase, during which basically the flow slows down and down and down until you get only a good small scale. You may have a big tumbling motion, but the velocities have gone down quite a lot. Here, it's not the case. As soon as you close the valves, you have to ignite right away because you're going to, you don't have that much time. So you will have to ignite in a very intense turbulence. And you will see that this is actually a big problem. We have seen in the turbulent combustion sessions that when turbulence is very intense, it's not good for combustion. You don't want it to be too intense. There's another problem also is that in a system like this, you don't really know where the residuals are going to be. The residuals are the burn gases of the previous cycle. They could get, they could stick somewhere and hide themselves there so that they are still present in the following cycle, and thereby they will also decrease the efficiency because they cannot burn twice, obviously. So here, what we did, of course, is to try to do LES to try to address these questions. So we're using, again, the same code. We have only one to do that, so it's always the same one. And the difficulty in this case is that we need to handle the rotation. So I'm going to describe the methodology we use for that. There are different methods to do moving meshes, Actually, I'm missing here the cut cell method of converge is another one that we don't have in our code. There's this classical ALE, which was in Kiva 25 years ago, where you take the meshes and stretch them, and that's what we used for the piston engines before. There's this method of immersed boundary conditions, where you have a fixed mesh, and you put the objects there, and you block the zone where the object is. That's not very far from the cut cell method of converge, actually. And this MESCOG method, which is the one I'm using, which is a chimera method, which I'm going to describe now. So what's the principle of the method that we used? We did all kinds of tests with these methods, but the most suitable method here was MESCOG. So MESCOG is a method where you actually use two AVBP at the same time. So one AVBP is running on the blue mesh, and another AVBP is running on the red mesh. And they have an overlap zone here. And in this overlapping zone, this is the small zone here, these two AVBP exchange information so that they can advance in time. So when this guy here needs to know the derivative, for example, he goes here and takes this one. So we need to know the velocity here. Okay, I get it from here. Same thing for this guy, needs the velocity here. He can take it from here. So the two meshes overlap a little bit. The nice thing about it then is that this one can turn and this one can be fixed. When you do the interpolation, this point will have moved later here. You just grab whatever data you find when you're turning. And these two things are fixed in their own reference frame. You don't need to change the mesh. So that's a very elegant way of doing the problem. And then, of course, to couple this thing, we have validated that for many other problems, academic cases. And one of the problems will be that in the experiments, we know we have leaks. And then the question is, how do you mimic the leaks of the experiment in the simulation? That's a tough one. And what we saw actually is that the method in itself here also has leaks. So we were able actually to tune the leaks by changing this distance here. By tuning this distance, we were able to adjust the leaks of the method, of the numerical method, to the leaks of the experiment. In the leakage zone here, as you can see, you have the overlap of the two methods. You can tune here by, actually what we do is we add a little bit of numerical viscosity there to slow the flow. And that's the way we can mimic by which we can mimic the leaks in the system. So let me show you now the comparison between LES and experiment. So we start with the cold flow. Now, since we have 4 moving objects, we need 4 instances of AVBP running simultaneously, and then we have a 5th instance for the fixed part. And all of this is, rotating at the same time. Now, same problem for boundary condition. This is the chamber. We compute the atmosphere, and we compute the tank here, so that we feel comfortable with the boundary conditions. Here, pressure is imposed, and here, pressure is imposed. So that's cool. No discussion about impedances, because they are included in the simulation. This is an idea of the various instances. So you have the 5 instances here, and the number of points for each of them. And remember now that these 5 instances will all work together, and they will be coupled using OpenPalm, that the software I've described before. We did not inject liquid fuel. We injected gas. In other words, we assumed that the vaporization was instantaneous. It was already complicated enough, so we said for the moment, let's just inject gas, and we inject octane in that case. And we have, apart from that, we respect the timing of injection, 1, 2, 3, 4. Okay, so the combustion model is always the second flame model. We don't change. This is the kinetic schemes. You've seen that many times now. You recognize the octane scheme for 2-step, which is good for the lean flames, not so good for the very rich flames, but still, it's quite reasonable. You don't need more at this point. We are not at the point where we want to compute NOx for this guy. We have a spark, so we model it again with this ED model where we deposit energy at one point over a certain time, and that will trigger the combustion. So let's look now at these different cases. The first one is a non-reactive case at 1200. Then we go to 1200 with combustion, and then 1500 with combustion. The non-reactive cases, this is the valve. Now this is the experiment, the mean value and the max value, and this is the LES. So this is one cycle of the LES. This is another cycle of the LES. And as you can see, we match the experiment really well. And like the experiment, we see that there is not much dispersion here. The system reproduces itself at every cycle. Yeah.
Intake pressure when we were and the fuel injected. So you actually injected in the experiments gas fuel or
The experiment was liquid.
so all the reasons I was asking is that modeling the injection rate, shape, and temperature. Vaporization very much depends on the rate shape. Because this is happening so fast, it can so happen that the pressure not evaporate.
Absolutely. And what we say is that vaporization is instantaneous, which is not true. And we know that actually the worst case here, the worst problem is this one. We should take that into account. But for the moment, we didn't do it.
Because you showed us some shooting flames,
Yeah,
and that's probably the reason.
that could be due to the two-phase flow. Actually, it's worse than that. We believe you have films, liquid films of fuel sticking to the walls, and that's another problem. But that's a problem. At that point, you have to wonder, we convinced actually the guys doing the experiment to come back to gaseous fuels for the moment, because the liquid jet make everything complicated. Actually, even for them, because they get liquid films on the windows, so they have to stop to clean them up. So again, at that point, it's just making the issues just too complicated.
What kind of the injection pressures would they
Well, for the liquid, I think they use the same pumps that you use for direct injection. So they got it from actually from an automotive company. So these are all the LES cycles, and we did 10 cycles. But since they are all the same, There's no reason to do more, and that was a good validation of the methodology we use for the movement of the mesh. And the leaks, if you look at the leaks here of the LES, they are of the same order than the leaks from the experiment. How did we do that? Well, we just tuned the size of the mesh, which is here, up until the point we got the same kind of losses. That's a big problem, I guess. In practice, modeling this kind of losses is tough. So in that case, it was easy, but I'm afraid it will be a problem later. So where do cyclic variations come from now if you go to combustion? Now this is a field of actual velocity starting when the valves are open here at the inlet and they're still open at the outlet. So if you look at that and you look at the movie here, you want to go, you don't want to go? Okay, so you see what you mentioned before. There is backflow first, it's going the wrong way, and then there's an inflow. Okay, backflow, now they open, you have an inflow, you still have something going out, then you close. Then you have the flame starting. It goes fast. This is how you see that you have to be fast for combustion. So the flame reaches the walls fast, so you have a very strong flame-wall interaction. Then you open the exhaust, you have a fast jet here with a shock actually at the outlet, and then you feed it again from the inlet. So you can watch this for a while. Initially, there were problems even in the experiment because the flame would flash back here. Here it does not do it because the timing is such that there is no flashback, but with this big jet, there could be actually. And here at the bottom, you have the isosurface of fuel in white and the isosurface of temperature in red, and the message is about the same. You can see now the fuel injection. Now the flame begins, it's getting out, and then you start again. You can see that the fuel mass fraction field is not that great. I mean, you have because you inject one after the other here, you start by the top, then the bottom. These things are moving in all directions because they are strong acoustic waves. So really, it's not a really clean flow field in which you have to ignite your flame. Okay, so if you look now at the curves, this is what we found. Ignition is here. This is the experiment. In the experiment, that's the mean pressure, the max pressure, and the lowest pressure. So when you do the LES, this is one cycle of LES. This is another one. This is another one, and you keep doing cycles. Some of them are really bad. This guy does not ignite at all. Some of them are reasonably good, and you see, they are all over the place here, but they are not very far from the experiment. What they show also is that the dispersion is very large. None of these cycles look the same, okay? So again, we have a lot of CCV here. Following what we did for engines, we knew that 25 cycles was a good guess, to start looking at cycle-to-cycle variations. So the LES is in the experimental envelope, and like the experiment, we found very important cycle-to-cycle variations. This is two-step chemistry. Two-step. So where do these things come from? One of the things we did is to look at the velocity magnitude in the chamber. From one cycle to other cycle, we just integrated the velocity field, the modulus, and we plot it here. So this is for one cycle. You see that when you open the inlet valve, you have a fast jet entering your system. Then when you close it, it decays. And when it finishes decay here, then we ignite. This is one cycle, this is another one, and you plot all the cycles, you find out that at the moment where you spark, the velocity can go from anywhere from 10 to 50 meters per second on average. In other words, in certain cases you ignite in a quiet flow, in other cases you ignite in a strongly turbulent flow. And that's, we believe, one of the sources of the problem in terms of cycle-to-cycle variation. But remember, we cannot wait because we don't have that much time here before we go to the next cycle. So what we started doing is to plot here the number of the cycles and here the maximum pressure, normalized by the inlet pressure. So when you see 1, it's a cycle which did not burn. When you see 3 or 4, it's a cycle which burned. And you see this pattern here that it seems very difficult to have a lot of cycles which burn. And for the LES here, we had this kind of pattern. And we saw that we could separate cycles in two, cycles which burn and cycles which don't burn. Okay. And there are many cycles which don't burn. And the experiment says the same thing. So there we have a big problem. Why do they burn? Actually, when we put here at the spark, this is the spark location, when you look at the velocity field, we see that for the non-burning cycles, we have on average a very large velocity at the spark. So again, it comes back to this idea that if you have a strong motion in this flow, it's a bad idea to ignite it because it can lead to quenching. Now, when you go back now to these cycles, I will just isolate 3 of them, C9, 10, and 11, and show you things during the cycle now. This is C9, C10, C11, and you see here the pressure curve. So that's a good cycle. Pressure goes up, good combustion. Then pressure goes down. Next cycle, no combustion at all. Next cycle, up, it goes up again. So it seems that really certain cycles are completely misfires. Now, if you look at the velocity in the combustion chamber for these cycles, you see actually that for the cycles which burnt well, we had a low velocity, and when the cycles quench, you have a large velocity. And that seems to be almost a reproducible pattern, that if you have a large velocity, you quench this flame. Why? Because if the velocity is of the order of 30 meters per second, and the flame speed is 30 centimeters per second, the flame will have a hard time, and it will be completely destroyed by turbulence. So we looked at the impact of the velocity. You can see here different movies. So that's the first one for C9. For C9, you see that combustion is extremely good and fast, but the flow velocity is less. Here, the flow velocity is small. We ignite in a flow where the velocity is not too much. And that helps to keep our pressure curve correctly and to go fast. So, which we go to the next example, which is C10. This one does not work the same way. Now you see that when we're going to ignite, we ignite in a very strongly turbulent flow. You can see here the velocity. So, moment where we ignite, nothing's happening. You have a very small kernel that you saw here. You're going to see it again, but it doesn't last, and the flame is quenched right away. Ignition is now. Okay? So you saw it, and then it went away. And for the last cycle, it's a little bit better. It's just a little bit slower too. So here, we ignite, and the kernel will develop. You see it here. We see it's more convected, but still it's able to, complete combustion. So you see that there seems to be a link between the initial velocity field and turbulence. Now, this is just to summarize the same thing. C9 at ignition, a little bit later, a very strong combustion, but low velocities. Here, more velocity, but then no combustion. And here, intermediate velocity and a reasonable flame, a little bit weak, but still doing okay. So we can actually classify our cycles in 2 groups then. We can look at the cycles which burn well and look at the cycles which do not burn well. Like you have a series here where you have 3 good cycles. Here you have a series where you get 1 cycle burning and the next one is not burning. And you can do, I don't know, you call that, in French we say phase portrait, a portrait in phase, You plug here cycle n, that's the pressure at cycle n, and here you put the pressure of cycle n plus 1. So if you are here, it really means that the previous cycle burned well and the following cycle is burning well. If you are here or there, it means the previous cycle burned well, but the next cycle is not burning well. And what you do for C9, C11, you were here, C9 is going to C10, is going to C11, so you have one cycle burning, the next one is not burning, then burning again, so you have an oscillation between these two. You would like to be here, of course, but you're not. Sometimes you are here or there. And so you start seeing something else here. You start seeing an idea that there is a link between following cycles. Not only they are different, but they are coupled. So that's a new mechanism that you don't see in engines, is that there is a correlation between cycles. So let me show you that. Before that, let me just also show the influence of residual gases. If you have residual gases in the chamber from the previous cycle, you will have a low pressure. In other words, C10, for example, has a lot of burnt gases there. It will have a low efficiency. Now, at that point where we did this study, we realized that we had a problem. We had two sources which could explain CCVs. One of them was that you have large values of velocity, it's bad for combustion. The other one is that if you have high value of residual gases, it's also bad. So which one is the source of CCV? There's one way to do it. We did another case. So we did OP3. OP3 is running faster, 1500 RPM. And you can see here the experiment. And the experiment tells you, wow, all these cycles are not burning. These cycles are burning, those are not burning. And the LES says the same thing, okay? You have a lot of cycles which are actually not burning at all. It's no combustion. So why is it so? Well, it's easy, actually. If you look at the velocity, you can check that this is the velocity here. And basically, if you have a low velocity at one cycle, you get a high pressure at the next one, and vice versa. You can actually plot a diagram, which is here, where here you put the velocity at the beginning of the cycle, and here you put the pressure. And you see that for all cycles where the velocity is more than 33 meters per second, you're sure you're going to have quenching. So that seems to be the most important parameter here. Cycle n-1 controls cycle n, because if you give to cycle n a large velocity, then it will quench. And that's very different from engines. Because in a piston engine, because of the compression phase, by the time you spark, you have forgotten the previous cycle. You know, you have a long time. You have intake, compression, everything's gone. Here it's not the case. Each cycle remembers what happened before. In other words, that explains also why cycles are very difficult to keep in the stable region. If you have a good cycle, it's very likely that then the next one will not be good. This is why we see this continuous oscillation. The reason for this is that if you have a good cycle, then it will induce large velocities for the following cycle, it will then be bad. So to conclude on this problem, it's really telling you that it's a good idea to do constant volume combustion chambers, but it's not going to be that simple, okay? It took 100 years to do piston engines. They're not going to do it in 2 days. And one of the first problems they will have is that they will have cyclic variations. They will have leaks. We have seen that already. And of course, the efficiency at the moment is not 30% more than what it was. It's like 50% less than what it was, okay? So it will take a long time to make progress there.
What was the shaft power intended to be taken out finally from the chamber? Was it a turbine or was it driving?
For the moment, this system should still be included in a gas turbine with a compressor and a turbine, okay? So the 3 bars will be more, it will be provided by the compressor. Is that the question you asked, or?
Yeah, because efficiency very much depends on that.
Sure. No, that was a laboratory system. Of course, in a real system, instead of 3 bars, you would have 30. But still, if it does not work for 3 bars, it's not going to work for 30. Now, we showed that you can investigate this thing with LES, and that's actually probably a good idea to do it now before building a new one. And we've seen that the LES allows to explain what we see in the experiment. These unstable mechanisms are different from real engines, because in IC engines, you see that we had perturbations which are not due to coupling between cycles. In the future, they're going to change that completely. They have a new design here. They didn't give up. There's a big project to try to do better. And it's actually a complicated problem. One additional problem for those of you who know turbines is that if this system works, then the turbine will be fed by an unsteady flow field. And you know that the turbine is not really designed for that, you know, because the flow rate is going from 0 to 1. And the turbine will have problems. So probably we'll have to compute the chamber and the turbine at the same time if you want to do that in a clean way. Okay, I think I'm going to stop here. I'm kind of late already. Any question? Well, that's the problem. If the Mach number is becoming too large, you will need to add more chambers to split the flow over a larger area, because you see here that the high velocities are already a problem. We cannot go to higher velocities. It will be too much. The flame will not be able to burn. So yes, you're right. If this has to go to higher velocities, there's a problem. There's no detonation here, okay? Yeah, you could imagine producing a detonation in this system, okay? Which in that case would be very efficient, but then the whole structure has to resist to pressures which are crazy pressures. This is what people have to study in rotating detonation engines, but that's a completely different field, because then you have to redesign the whole engine. People look at it, you know, all these things, the plans in Safran, for example, when they talk about that, they say it's something flying in 2045. Okay, so still, we still have time to think about it. I'm not sure it's ever going to work. Huh?
Let's forget cycle-to-cycle variations for the moment. So in a single cycle, were any simulations ever done to see the exact perturbations in pressure places that were observed in actual experiments? In a single cylinder cycle, because that's very much essential for now of an engine.
Yeah.
That's essentially the main thing is control.
Well, first, we cannot compare the LES and the experiments cycle by cycle, because we would not know which one to compare to which one. In individual cycles in the LES, we have all the fields, okay? We know what's going on, but that it's difficult to look, when you look at one cycle, it's difficult to say what's going wrong for this cycle. It just looks normal. What we see is that certain of them do not ignite. That's all you can say. So is this one more normal than that one, or this one? It's turbulent, so they are all different. That's the only thing we can see.
I'm not saying that we should be comparing it with the experimental data. What I'm interested in is does LES I shouldn't be saying capture experimental. Does
Yeah.
LES even show, let's say, small perturbations in pressure resistance of the spark ignition engines?
Yes, LES captures turbulent motions, so as such, it will create all these perturbations that you see. But at the same time, it does not really tell you why, you know. You see them, they are here, you have the turbulence. But what to do with that is another problem, you know. How do you handle that? You just know that you can capture the experiment. After that, it's tough. I will talk actually tomorrow about the reproducibility of turbulent computations with LES. You will see how these things can diverge, you know. So for the moment, we don't know. It's difficult to analyze those things at the moment.
So the acoustics of, all the previous experiments you did show the acoustic results as well. Here the acoustics are not analyzed.
No, I think they are. We just didn't start to look at them, but the acoustics of the plenum here are certainly important. When you see the backflow here, the backflow is controlled by the acoustics. Huh? When you look at the movie here, we see that if there would be a counter pressure, if the acoustic wave was tuned better, you know, this is what you do in engines. Huh? In an engine, you tune this thing so that the back pressure arrives at the right time. Here, it's not a good idea to have this, when at this moment, now, this thing should not be there. If you tune the length here in the right way, then the pressure wave will arrive here, the reflected pressure wave will arrive at the right time to say, no, don't go out, stay here. This is what you do in an engine. Huh? They haven't done that yet. They haven't even thought about it. For the moment, it's just, you know, very preliminary result. Actually, this system does not exist anymore. They have built 2 more generations now to try to fix all these problems because obviously this is not going to work. But you know, you learn things. It's okay. Any other question? If not, we meet tomorrow morning at 9 again. Last day. You can stop working after that. Or go back to work. I don't know which one is the best. Okay, have a good evening.